Okay, vectors indicate direction and scalars do not. So some examples of vectors: velocity, acceleration, and scalars, temperature, time, and speed. So as an example,
Kayla Moe, Connor Hanksleben, and Colton Ricard to the office.
velocity and speed are different because velocity would indicate a direction. So a speed might be 60 miles per hour, but a velocity would be 60 miles per hour south or something like that. Vectors can be added graphically. We're going to try for scale. We'll try to make a 100-meter vector twice as long as a 50-meter vector, or whatever the vector happens to be. Vectors can be moved parallel to themselves in a diagram. So for instance, if I were going to add these two vectors to each other, I actually can't add them that way. I have to do tip to tail, and we're going to show that in just a minute. So what I could do is I can move this particular one right here over, and that's the proper way to add the vector. So I just moved this guy over parallel, and that's fine. Vectors can be added in any order. You must do tip to tail. We'll look at that, and the resultant vector will be the same. And vectors can be anything. You can have velocity vectors, meters per second, displacement vectors in meters, acceleration, meters per second squared. You could have force, which is in newtons, pretty much anything. We're going to add vectors tip to tail. We draw in the resultant vector from the tail of the first to the tip of the last. So let's say that we have several vectors. We have A, we have vector B, whatever it is, distance, velocity, whatnot, and we have vector C. So vector C obviously has a greater magnitude than vector A or B, and vector A and B are about the same magnitude. So if I were to go ahead and add A plus B plus C, what would happen is I would go A plus B, notice it's tip to tail, plus C. So A plus B plus C. The resultant vector would be then from the tail of this one to the tip of that one, and that would be your resultant vector. Now look what happens if I go A plus C plus B. So in this is a different order. So I'm going to go A, but instead of doing B, I'm going to put the C in, and then I'm going to put the B in. Notice that we get the same resultant vector. So it doesn't matter which order you do it in, okay? Now they don't look exactly the same, but I was just freehanding the stuff. Okay. When we subtract vectors, we're, again, tip to tail, but first we multiply the vector to be subtracted by a -1, and that basically keeps the magnitude but reverses the direction. So let's just do an example here. Vector A is 3 meters due east. Okay, that's vector A. And then I'm going to go 45 degrees. I'm not going to continue. I'm going to go 45 degrees, 8 meters north of due east. So I'm going to go 45 degrees north of due east. Okay, if I kept going east, it would be like this, but I'm going to go 45 degrees north of that. The resultant vector then is going to be right there, and that's the resultant vector. Now if I were to subtract those,
Can I have your attention, please? The Future Teachers Club is meeting in Ms. Herman's room at this time.
okay. If I were to subtract it, that's A plus B. What if I were to do A minus B? Well, what I would do is I would draw A due east, and, gosh, I don't think I have enough room. I'm going to do it up here. And then what I'm going to do is actually put B down like this. I'm going to go 45 degrees in the opposite direction. So instead of north of east, I'm going to go south of west. And that's how you subtract it. And then the resultant vector would be right there. Okay, so that's subtracting. We can graphically add vectors. We could actually take out a ruler and a protractor and make up a scale. and then we would draw them in with the correct angles and the distances, and we draw a resultant vector, and then we would measure that resultant vector and convert it back to meters, and we would take the protractor and we would measure the degrees, and we would know how to describe it. We're going to do that with the treasure map, but for everything else, we're going to do mathematics to get it. So remember SOHCAHTOA, and let's just do a couple here. So we have an archaeologist climbing a pyramid. So here's a pyramid. And let's say they climb up like so. They're on top of the pyramid. And we want to know what's that resultant vector. This is the resultant. And we know that this is 230 meters wide. So I'm going to make this 115 meters here, 115 meters here. And then it's 136 meters tall. And so obviously what you can do, because this is a right triangle, is do the Pythagorean theorem and get the magnitude. Okay? So when you do that calculation, you are going to get 178 meters. Make sure you realize it's meters because we started with meters. And then we're going to want to have angles. So we're going to say the tangent of theta is 136 over 115. And we do the inverse tangent, and we're going to get 49.8 degrees. And that 49.8 degrees, we have one more thing we have to talk about. That's that angle right there is what we're doing. And we would say, probably with this one, above the horizontal. If this were a map, I'd probably say north of directly east. So this is east. I'm going to go 49.8 degrees north of that. Okay, but because it's a pyramid, I'll just say above. Okay, so another one. I'm going to go east, 1,540 kilometers. And then I'm going to go north, again, notice tip to tail, 1,160 kilometers. The resultant vector is right there, and the angle. So again, I'm going to do the Pythagorean theorem, and I'm going to take 1,160 squared plus 1,540 squared, take the square root of that, and my resultant vector here, when I do that, should be 1,930 kilometers. Notice the kilometers. And then if I go tangent of theta is equal to 1,160 over 1,540, if I do the tangent function for that, I should get 37 degrees. And I'm going to indicate it as that many degrees north of east. Okay. This is another one where we have a box and we have two forces being applied. One is 760 newtons, so now we have a newtons as our our vector. And that is not tip to tail. We've got two forces pulling or pushing on a box. So what I'm going to do is just redraw them tip to tail. Oops. And then what happens is the resultant vector is like that. And we can get V, oops, that's newtons, 500 newtons. And then we can go ahead again with the Pythagorean theorem, 760 squared plus 500 squared, square root of that. We're going to get a resultant vector here of 900 newtons. I'm rounding it to 1 sig fig. If I do tangent of theta is equal to 500 over 760, I'll get an angle of 30 degrees, and it will be south of west. So that would be south of west over here. South. Okay. Resolving a vector into components. Let's say that I have a plane. It's a pretty bad plane, but get the idea. Flying 35 degrees to the ground. And I have a truck. And the question is,
Staff meeting in the West Lecture Room at this time. Staff meeting in the West Lecture Room.
okay, breaking it up into the two components, I am looking for the x component here. And this is 95 kilometers per hour. So what I'm going to use is the cosine of 35 is going to equal x over 95. So I'm actually calculating how fast that truck must go. And if you calculate that out, you should get 78 kilometers per hour. Okay. And there's a few more examples, so but you get the right idea, the idea of what's going on. And then in the second video, I'll do non-right triangles.